Bohrium. Bohrium is a synthetic chemical element with symbol Bh and atomic number 107. It is named after Danish physicist Niels Bohr. As a synthetic element, it can be created in a laboratory but is not found in nature. It is radioactive. Its most stable known isotope, 270Bh, has a half-life of approximately 61 seconds, though the unconfirmed 278Bh may have a longer half-life of about 690 seconds. In the periodic table of the elements, it is a d-block transactinide element. It is a member of the 7th period and belongs to the group 7 elements as the 5th member of the 6D series of transition metals. Chemistry experiments have confirmed that barium behaves as the heavier homologue to rhenium in group 7. The chemical properties of barium are characterized only partly, but they compare well with the chemistry of the other group 7 elements. Two groups claimed discovery of the element. Evidence of barium was first reported in 1976 by a Soviet research team led by Yuri Gagansyan, in which targets of bismuth-209 and lead-208 were bombarded with accelerated nuclei of chromium-54 and manganese-55 respectively. Two activities, one with a half-life of 1 to 2 milliseconds, and the other with an approximately 5-second half-life, were seen. Since the ratio of the intensities of these two activities was constant throughout the experiment, it was proposed that the first was from the isotope barium-261 and that the second was from its daughter dubnium-257. Later, the dubnium isotope was corrected to dubnium-258, which indeed has a 5-second half-life. However, the half-life observed for its parent is much shorter than the half-lives later observed in the definitive discovery of barium at Darmstadt in 1981. The IUPAC/IUPAC transfermium working group concluded that while dubnium-258 was probably seen in this experiment, the evidence for the production of its parent barium-262 was not convincing enough. In 1981, a German research team led by Peter Armbruster and Gottfried Munzenberg at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt bombarded a target of bismuth-209 with accelerated nuclei of chromium-54 to produce 5 atoms of the isotope barium-262. This discovery was further substantiated by their detailed measurements of the alpha decay chain of the produced barium atoms to previously known isotopes of fermium and californium. The IUPAC/IUPAC transfermium working group recognized the GSI collaboration as official discoverers in their 1992 report. In September 1992, the German group suggested the name Niels Bohrium with symbol NS to honor the Danish physicist Niels Bohr. The Soviet scientists at the Joint Institute for Nuclear Research in Dubna, Russia had suggested this name be given to element 105, and the German team wished to recognize both Bohr and the fact that the Dubna team had been the first to propose the cold fusion reaction to solve the controversial problem of the naming of element 105. The Dubna team agreed with the German group's naming proposal for element 107. There was an element naming controversy as to what the elements from 104 to 106 were to be called. The IUPAC adopted unilseptium as a temporary, systematic element name for this element. In 1994, a committee of IUPAC recommended that element 107 be named barium, not Niels Bohrium, since there was no precedence for using a scientist's complete name in the naming of an element. This was opposed by the discoverers as there was some concern that the name might be confused with boron, and in particular the distinguishing of the names of their respective oxyanions, barate and borate. The matter was handed to the Danish branch of IUPAC which, despite this, voted in favor of the name barium, and thus the name barium for element 107 was recognized internationally in 1997. The names of the respective oxyanions of boron and barium remain unchanged despite their homophony. Barium has no stable or naturally occurring isotopes. Several radioactive isotopes have been synthesized in the laboratory, either by fusing two atoms or by observing the decay of heavier elements. 12 different isotopes of barium have been reported with atomic masses 260, 262, 264, 267, 270, 272, 274, and 278, one of which, barium-262, has a known metastable state. All of these but the unconfirmed 278Bh decay only through alpha decay, although some unknown barium isotopes are predicted to undergo spontaneous fission. The lighter isotopes usually have shorter half-lives of under 100 ms for 260Bh, 261Bh, 262Bh, and 262MBh were observed. 264Bh, 265Bh, 266Bh, and 271Bh are more stable at around 1s, and 267Bh and 272Bh have half-lives of about 10s. The heaviest isotopes are the most stable, with 270Bh and 274Bh having measured half-lives of about 61s and 40s respectively, and the even heavier unconfirmed isotope 278Bh appearing to have an even longer half-life of about 690s. The proton-rich isotopes with masses 260, 261, and 262 were directly produced by cold fusion. Those with mass 262 and 264 were reported in the decay chains of meitnerium and runconium, while the neutron-rich isotopes with masses 265, 266, 267 were created in irradiations of actinide targets. The 5 most neutron-rich ones with masses 270, 271, 272, 274, and 278 appear in the decay chains of 282NH, 287MC, 288MC, 294TS, and 290FL respectively. These 11 isotopes have half-lives ranging from about 10 milliseconds for 262MBh to about 1 minute for 270Bh and 274Bh, extending to about 12 minutes for the unconfirmed 278Bh, one of the longest-lived known super-heavy nuclides. Barium is the 5th member of the 6D series of transition metals and the heaviest member of Group 7 in the periodic table, below manganese, technetium, and rhenium. All the members of the group readily portray their group oxidation state of +7 and the state becomes more stable as the group is descended. Thus barium is expected to form a stable +7 state. Technetium also shows a stable +4 state whilst rhenium exhibits stable +4 and +3 states. Barium may therefore show these lower states as well. The higher +7 oxidation state is more likely to exist in oxyanions, such as perbarate, BHO4, analogous to the lighter permanganate, pertechnetate, and paranate. Nevertheless, barium is likely to be unstable in aqueous solution, and would probably be easily reduced to the more stable barium. Technetium and rhenium are known to form volatile heptoxides M2O7. So barium should also form the volatile oxide BH2O7. The oxide should dissolve in water to form perbaric acid, HbHO4. Rhenium and technetium form a range of oxyhalides from the halogenation of the oxide. The chlorination of the oxide forms the oxychlorides MO3Cl, so BHO3Cl should be formed in this reaction. Fluorination results in MO3F and MO2F3 for the heavier elements in addition to the rhenium compounds ReOF5 and ReF7. Therefore, oxyfluoride formation for barium may help to indicate EKA rhenium properties. Since the oxychlorides are asymmetrical, and they should have increasingly large dipole moments going down the group, they should become less volatile in the order TCO3Cl ReO3Cl BHO3Cl. This was experimentally confirmed in 2000 by measuring the enthalpies of adsorption of these 3 compounds. The values are for TCO3Cl and ReO3Cl are 51 kJ/mol and 61 kJ/mol respectively. The experimental value for BHO3Cl is 77.8 kJ/mol, very close to the theoretically expected value of 78.5 kJ/mol. Barium is expected to be a solid under normal conditions and assume a hexagonal close-packed crystal structure, similar to its lighter congener rhenium. It should be a very heavy metal with a density of around 37.1 G/cm3, which would be the third highest of any of the 118 known elements, lower than only meitnerium and hassium, the 2 following elements in the periodic table. In comparison, the densest known element that has had its density measured, osmium, has a density of only 22.61 G/cm3. This results from barium's high atomic weight, the lanthanide and actinide contractions, and relativistic effects, although production of enough barium to measure this quantity would be impractical, and the sample would quickly decay. The atomic radius of barium is expected to be around 128 pm due to the relativistic stabilization of the 7s orbital and destabilization of the 6d orbital. The BH end ion is predicted to have an electron configuration of 5f146d47s2, giving up a 6d electron instead of a 7s electron, which is the opposite of the behavior of its lighter homologues manganese and technetium. Rhenium, on the other hand, follows its heavier congener barium in giving up a 5d electron before a SiXs electron, as relativistic effects have become significant by the 6th period, where they cause among other things the yellow color of gold and the low melting point of mercury. The Bh2+ ion is expected to have an electron configuration of 5f146d37s2, in contrast, the Re2+ ion is expected to have a 4f145d5 configuration, this time analogous to manganese and technetium. The ionic radius of hexacoordinate heptavalent barium is expected to be 58 pm. Pentavalent barium should have a larger ionic radius of 83 pm. In 1995, the first report on attempted isolation of the element was unsuccessful, prompting new theoretical studies to investigate how best to investigate barium and removing unwanted contaminating elements such as the trivalent actinides, the group 5 elements, and polonium. In 2000, it was confirmed that although relativistic effects are important, barium behaves like a typical group 7 element. A team at the Paul Scherrer Institute conducted a chemistry reaction using 6 atoms of 267Bh produced in the reaction between 249Bk and 22Ne ions. The resulting atoms were thermalized and reacted with a HCl/O2 mixture to form a volatile oxychloride. The reaction also produced isotopes of its lighter homologues, technetium and rhenium. The isothermal adsorption curves were measured and gave strong evidence for the formation of a volatile oxychloride with properties similar to that of rhenium oxychloride. This placed barium as a typical member of group 7. The adsorption enthalpies of the oxychlorides of technetium, rhenium, and barium were measured in this experiment, agreeing very well with the theoretical predictions and implying a sequence of decreasing oxychloride volatility down group 7 of TCO3Cl ReO3Cl BHO3Cl. The longer-lived heavy isotopes of barium, produced as the daughters of heavier elements, offer advantages for future radiochemical experiments. Although the heavy isotope 274Bh requires a rare and highly radioactive berkelium target for its product, the isotopes 272Bh, 271Bh, and 270Bh can be readily produced as daughters of more easily produced muscovium and nihonium isotopes.